Hello student, welcome to EPG Pathshala. I am Anchal Srivastava from Department of Physics, Institute of Science, Banaras Hindu University. Today we are going to discuss about module titled Ultraviolet Visible Absorption Spectroscopy, which is also known as UV Vis Spectroscopy, under the paper Nanoscience and Technology 2. After completing this module, the student will able to learn a few basic ideas about electromagnetic spectrum and principle of spectroscopy. You will also know the UV vis spectroscopy and its theory. You will learn the construction and working principle of UV visible spectrophotometer and know the electronic transition and application of UV visible spectroscopy. The spectrophotometer has well been called the workhorse of a modern laboratory. In particular, ultraviolet and visible spectroscopy is the method of choice in most of the laboratory concerned with the identification and measurement of organic and inorganic compounds in a wide range of products and processes. In nucleic acid, protein, foodstuff, pharmaceuticals, fertilizers, in mineral oil, in paint, in every branch of molecular biology, medicine, and the life science, the spectrophotometer is an essential add to both research and routine control. Ultraviolet and visible spectrometer have been in general used for last 35 years and over this period have been the most important analytical instrument in the modern day laboratory. In many applications, other techniques could be employed but not rival UV visible spectroscopy for its simplicity, versatility, speed, accuracy, and cost effectiveness. UV visible spectroscopy is the measurement of the wavelength and intensity of absorption of near ultraviolet and visible light by a sample. Ultraviolet and visible light are energetic enough to promote outer electron to higher energy levels. UV visible spectroscopy is usually applied to molecule and inorganic ions or complex in solution. The UV visible spectra have broad features that are limited use of sample identification but are very useful for quantitative measurements. The concentration of an light in solution can be determined by measuring the absorbance at some wavelength and apply the Beer-Lambert law. Electromagnetic spectrum. The molecular spectroscopy is the study of the interaction of electromagnetic wave with matter. The propagation of these radiations involves both electric and magnetic forces, which gives rise to their common class named electromagnetic radiation. In spectroscopy, only the effect associated with electric components of electromagnetic wave are important. The electromagnetic spectrum is arbitrarily divided into various regions, and it is clear that the familiar visible portion of the spectrum of the order or the range 390 to 750 nanometer constitutes only a small section of the full spectrum. The visible region is flanked by higher energy ultraviolet UV and lower energy infrared and microwave regions. These frequency ranges are the most widely used in spectroscopic measurements, as they can each provide key structural insight into analytes molecules. The microwave region of the electromagnetic spectrum is associated with rotational spectroscopy, while the UV and visible portion correspond to molecular electronic transition. The IR region, which is typically broken into near, mid and far IR, is utilized in vibrational spectroscopy, as the frequency of radiation therein correspond to molecular vibrations. Let us discuss the principle of spectroscopy. Spectroscopy is the study of the way electromagnetic radiation and matter affect each other. Think of way light is affected when it hits a glass prism. When white light hits the glass prism, it splits into rainbow, a color of colors. In general, matter is exposed to electromagnetic radiation. For example, infrared light, the radiation can be absorbed, transmitted, reflected, scattered, or undergo photoluminescence. By doing this, you can figure out how intense light is in those various wavelengths. The device we use in spectroscopy are usually called spectrometers. Spectroscopy is important in history because it paved the way for quantum mechanics. It allows us to better understand electromagnetic radiation like light. Using these observations, we were able to explain back-body radiation, the photoelectric effect, and the structure of atom. The UV visible spectroscopy. When radiation interacts with matter, a number of processes can occur, including reflection, scattering, absorbance, fluorescence, phosphorescence, which is absorption and re-emission, and photochemical reactions, absorption and bond breaking. In general, when measuring UV visible spectra, we want only absorbance to occur because light is a form of energy. Absorption of light by matter causes the energy content of the molecules or atom to increase. The total potential energy of the molecule generally is represented as the sum of its electronic, vibrational and rotational energy, which is E total is equal to E electronic plus E vibrational plus E rotational. The amount of energy a molecule possesses in each form is not a continuum, but a series of discrete levels of state. The differences in energy among the different states are in the order of E electronics is greater than E vibrational is greater than E rotational. The absorption process depends upon an atomic structure in which each of the electron of an atom has an energy level associated with its position in the atom. Permitted energy levels are finite and well defined, but an electron may be made to change to another level if the quantum of energy is delivered equal to the energy difference between these two labels. The original level is called the ground state and the induced level is known as excited state. Excited states are generally unstable and electron will rapidly revert to the ground state, losing the acquired energy in the process. While the accepted model of atomic and molecular structure has arises from the wave mechanical treatment of Schrödinger, it is convenient to imply an earlier method, that of Bohr, in order to explain more simply the electronic phenomena of interest in spectroscopy. The theory of UV visible spectroscopy. Each electron in a molecule has a unique ground state energy, and The discrete level to which it may jump are also unique. It follows that there will be a finite and predictable set of transitions possible for the electron of a given molecule. Each of the transitions or jump require the absorption of a quantum of energy, and if that energy is derived from electromagnetic radiation, there will be a direct and a permanent relationship between the wavelength of the radiation and a plot of those points along the wavelength scale at which a given substance shows absorption peaks or maxima is called an absorption spectrum. If a particular wavelength of UV or visible radiation can be isolated from the source and passes through a sample which can absorb some of the radiation, then the transmitted light intensity IT will be less than the incident light intensity I0. The amount of light transmitted with respect to the incident light is called transmittance T, and this can be written as T equal to IT by I0. Sample can absorb all or none of the incident light, and therefore transmittant often quoted as percentage. So percentage transmittance is equal to IT by I0 into 100. By plotting the absorbance versus wavelength, an absorbance spectrum is generated. The absorbance spectrum for a same compound A and B are shown, with the advantage that absorbance measurements are usually linear with concentration. Absorbance spectra are now used. Law of spectrophotometry. The greater the number of molecules that absorbs light on a given wavelength, the greater the extent of light absorption, and higher the peak intensity in absorption spectrum. If these are the only few molecules that absorbs radiation, the total absorption of energy is less and consequently lower intensity peak is observed. This makes the basis of B-Lambert law, which states that the fraction of incident radiation absorbed is proportional to the number of absorbing molecules in its path. When the radiation passes through a solution, the amount of light absorbed or transmitted in an exponential function of the molecular concentration of the solute and also a function of length of path of radiation through the sample. Therefore, A is equal to ECL, where C is the concentration of solute in mole, L is the path length of the sample in centimeter, and E is the molar absorbability or the molar extinction coefficient of the substance whole light absorbed is under investigation. It is a constant and a characteristic of a given absorbing species. Molecules are ions in a particular solvent at a particular wavelength. Psilon is the numerically equal to the absorbance of the solution of unit molecule concentration for C is equal to 1 in a cell of unit length L is equal to 1 and its unit are liters, mole inverse, centimeter inverse. However, it is customary practice among organic chemists to omit the unit. The working principle. Instruments for measuring the absorption of UV visible radiation are made up of following components. First is the source, which is UV and visible light source. The wavelength selectors, which is monochromator. Sample containers, detectors, and single processor and readout. Let us talk about the source, which is the UV and visible. The requirement are that the source should be stable during the measurement period, that the intensity of emitted radiation should not fluctuate, and that there should be adequate intensity over at a large wavelength region as possible. Ultraviolet light is generally derived from a deuterium arc that provided emission of high intensity and adequate continuity in the range of 190 to 380 nanometer range. A quartz or the silica envelope is necessary not only because of the heat generated but also to transmit the shorter wavelength of the ultraviolet radiation. The limiting factor is normally the lower limit of atmospheric transmission at about 190 nanometer. Visible light is normally supplied by a tungsten lamp or in modern system by tungsten halogen, also described as quartz iodine lamp, which has higher relatively output in the crossover region of 320 to 380 nanometer. The long wavelength limit is usually the cutoff of the glass or quartz envelope, normally well beyond the useful visible limit of 900 nanometer. Wavelength selectors, which is the monochromator. Polychromatic radiation of more than one wavelength enters the monochromator through the entrance slit. The beam is collimated and then strikes the dispersing element at an angle. The beam is split into the component wavelengths by grating or prism. By moving the dispersing element or in the exit slit, radiation of only a particular wavelength leaves the monochromator through the exit slit. Cuvette. The container for the sample and reference solution must be transparent to the radiation which will pass through them. Quartz or fused silica cuvettes are required for spectroscopy in the UV region. These cells are also transparent in the visible region. Silicate glass can be used for the manufacture of cuvettes for use between 350 to 2000 nanometer. Detectors. Let us talk about detectors. The photomultiplier tube is a commonly used detector in UV visible spectroscopy. It consists of photoemissive cathode, a cathode which emits electron when struck by the phonons of radiation. Several diodes which emits several electrons for each electron escaping to them, and an anode. The photon of radiation entering the tube strikes the cathode, causing the emission of several electrons. These electrons are accelerated towards the first diode, which has 90 volt more positive than the cathode. The electrons strike the first diode, causing the emission of several electrons for each incident electron. These electrons are then accelerated towards the second diode to produce more electrons, which are accelerated towards diode 3 and so on. Eventually, the electrons are collected at the anode. By this time, each original photon has produced 10 to the power 6 to 10 to the power 7 electrons. The resulting current is amplified and measured. Let us talk the electronic transitions. Electron in the atom can be considered as occupying groups of roughly similar energy levels. In the more complicated molecular model, electrons associated with more than one nucleus. The so-called bonding electrons are particularly susceptible to energy level transition under the stimulus of appropriate radiation. The electron concerned, usually p-type electrons in the first or second cell, may be present in one or two conditions. Sigma is localized bond with a low probability of transition, therefore of absorption, or pi, where the transition probability is much higher. The presence of a carbon-carbon double bond in a molecule increases the likelihood of pi-type bond, especially when conjugated double bonds are involved. Double bonds that alternate with the single bond. The effect is still greater in the presence of nitrogen. Chemical bonds are formed by overlapping atomic orbitals that results in molecular orbitals of one or three types: bonding, low energy; antibonding, high energy; and non-bonding. Energy absorption is most typically associated with transition induced in electron involved in bonding orbital, and the atoms involved are for the most part those containing s plus p electron. Two types of bond must be mentioned: sigma bond with its related antibody orbital designed at sigma star, and pi bond with the corresponding pi star antibonding orbital. The uninvolved n non-bonding electrons have not antibody orbitals. There are some transition lies: sigma to sigma star transition, n to sigma star transition, n to pi star transition, and pi to pi star transition. We will go one by one in detail. In sigma to sigma transition, an electron in the bonding orbital is excited to the corresponding antibody orbital. The energy required is large. For example, methane, which has only CH bond and can only undergo sigma to sigma transition, shows an absorption maxima at 1 to 5 nanometer. Absorption maxima due to sigma star transition are not seen in typical UV spectrum of 200 to 700. N to sigma star transition. Saturated compound containing atoms with lone pair non-bonding electrons are capable of n to sigma star transition. These transitions usually need less energy than sigma to sigma star transition. They can be initiated by light whose wavelength is the range of 150 to 250 nanometer. The number of organic functional groups with n to sigma star peak in the UV range is small. N to pi star and pi to pi star transition. Most absorption spectroscopy of organic compound is based on transition of n or p electron to the pi star state. This is because the absorption peak for these transitions fall in experimentally convenient region of the spectrum of 200 to 700 nanometer. These transitions need to unsaturated group in the molecule to provide the p electron. Molar absorbivities from n to pi star transition are relatively low and range from 10 to 100 liter per mole centimeter inverse. Pi to pi transition normally give molar absorbivity between 1000 to 10,000 liter mole inverse per centimeter inverse. The solvent in which the absorbing species is dissolved also have an effect on the spectrum of the species. Peak resulting from n to pi star transition are shifted to the shorter wavelength, the blue shift, with increasing solvent polarity. This arises from the increased solvation of the lone pair, which lowers the energy of the n orbital. Often, but not always, the reverse rate shift is also seen for pi to pi star transition. This is caused by the attractive polarization forces between the solvent and the absorber, which lower the energy level of both the excited and unexcited states. This effect is greater for the excited state, and so the energy difference between the excited and unexcited state is slightly reduced, resulting in a small rate shift. This effect also influences n to pi star transition, but is overshadowed by the blue shift resulting from the solvent of lone pair. Let us discuss the application of UV visible spectroscopy. The application of UV visible is in various fields. In molecular spectroscopy based upon UV visible radiation, it is used to identification and estimation of inorganic, organic, and biomedical species. In molecular UV absorption spectroscopy is employed primarily for quantification analysis. In UV visible spectroscopy, probably more widely used to chemical and clinical laboratories throughout the world than any other single method. So, a student, let us summarize what we have learned in this module. Ultraviolet visible radiation has the property of being able to promote an electron to a higher energy level. The Beer-Lambert's law is used to relate the absorption of UV visible radiation to the concentration of the substance, the path length of the cell, and the molar absorption coefficient. Molecules containing pi electron or non-bonding electron can absorb the energy in the form of ultraviolet or visible light to excite these electrons to higher anti-bonding molecular orbitals. The more easily excited the electron, the longer the wavelength of light it can absorb. Based on the fact of 4 types of transition, which is pi pi star, n pi star, sigma pi sigma sigma star, and n sigma star, the energy required for various transitions obeys the following order: sigma sigma star is greater than n sigma star is greater than pi sigma, pi pi star is greater than n pi star. This is all about UV visible spectroscopy. Thank you very much.